Stress-strain curves are an extremely important graphical measure of a material's mechanical properties. However, they are not without some subtlety, especially in the case of ductile materials that can undergo substantial geometrical change during testing. Stress is a quantity that describes the distribution of internal forces within a body. It is a measure of the internal force per unit area, so it has units of newtons per meter squared in SI units, and pounds per square inch in US units. Newtons per meter squared are also called pascals. Stress calculation is important because it allows us to predict when an object will fail. On the other hand, strain is quantity that describes the deformations that occur within a body. Strain is a non-dimensional quantity and is often expressed as a percentage. Normal strain can be tensile or compressive. Material stress and strain are closely linked. The relationship between the two can be described using a stress-strain diagram. Stress-strain diagrams are different for different materials. One can obtain the diagram for a specific material by performing a tensile test. This involves applying a known force to a test piece and measuring the stress and strain in the test piece as the applied force is increased. Perhaps the most important test of a material's mechanical response is the tensile test. Stress-strain testing, as well as almost all experimental procedures in mechanics of materials, is detailed by standards setting organizations, notably the American Society for Testing and Materials ASTM. Tensile testing of metals is prescribed by ASTM Test E8, plastics by ASTM D638, and composite materials by ASTM D3039, in which one end of a rod or wire specimen is clamped in a loading frame, and the other subjected to a controlled displacement, delta. A transducer connected in series with the specimen provides an electronic reading of the load P delta corresponding to the displacement. Alternatively, modern servo-controlled testing machines permit using load rather than displacement as the controlled variable, in which case the displacement delta P would be monitored as a function of load. The engineering measures of stress and strain are determined from the measured load and deflection using the original specimen, cross-sectional area A0 and length L0As, stress equals load P divided by cross-sectional area A0. In other words, stress is the force applied to a material, divided by the material's cross-sectional area. Similarly, strain equals displacement delta divided by length L0. Or strain is the deformation or displacement of material that results from an applied stress. When the stress is plotted against the strain, an engineering stress-strain curve such is obtained. In the early, low-strain portion of the curve, many materials obey Hooke's law to a reasonable approximation, so that stress is proportional to strain, with the constant of proportionality being the modulus of elasticity, or Young's modulus. As strain is increased, many materials eventually deviate from this linear proportionality, the point of departure being termed the proportional limit. This nonlinearity is usually associated with stress-induced plastic flow in the specimen. Here the material is undergoing a rearrangement of its internal molecular or microscopic structure, in which atoms are being moved to new equilibrium positions. This plasticity requires a mechanism for molecular mobility, which in crystalline materials can arise from dislocation motion. Materials lacking this mobility, for instance by having internal microstructures that block dislocation motion, are usually brittle rather than ductile. The stress-strain curve for brittle materials are typically linear over their full range of strain, eventually terminating in fracture without appreciable plastic flow. These microstructural rearrangements associated with plastic flow are usually not reversed when the load is removed, so the proportional limit is often the same as, or at least close to the material's elastic limit. Elasticity is the property of complete and immediate recovery from an imposed displacement on release of the load, and the elastic limit is the value of stress at which the material experiences a permanent residual strain that is not lost on unloading. The residual strain induced by a given stress can be determined by drawing an unloading line from the highest point reached on the stress-strain curve at that stress back to the strain axis, drawn with a slope equal to that of the initial elastic loading line. This is done because the material unloads elastically, there being no force driving the molecular structure back to its original position. A closely related term is the yield stress. This is the stress needed to induce plastic deformation in the specimen. Since it is often difficult to pinpoint the exact stress at which plastic deformation begins, the yield stress is often taken to be the stress needed to induce a specified amount of permanent strain, typically 0.2%. The apparent change from strain hardening to strain softening is an artifact of the plotting procedure, however, as is the maximum observed in the curve at the ultimate tensile strength, UTS. Beyond the yield point, molecular flow causes a substantial reduction in the specimen cross-sectional area, so the true stress actually borne by the material is larger than the engineering stress computed from the original cross-sectional area. The true stress is not quite uniform throughout the specimen, and there will always be some location, perhaps a nick or some other defect at the surface, where the local stress is maximum. Once the maximum in the engineering curve has been reached, the localized flow at this site cannot be compensated by further strain hardening, so the area there is reduced further. This increases the local stress even more, which accelerates the flow further. This localized and increasing flow soon leads to a neck in the gauge length of the specimen. Until the neck forms, the deformation is essentially uniform throughout the specimen, but after necking, all subsequent deformation takes place in the neck. The neck becomes smaller and smaller, local true stress increasing all the time until the specimen fails. The polymer, however, differs dramatically from ductile metal in that the neck does not continue shrinking until the specimen fails. Rather, the material in the neck stretches only to a natural draw ratio, which is a function of temperature and specimen processing, beyond which the material in the neck stops stretching and new material at the neck, shoulders, necks down. The neck then propagates until it spans the full gauge length of the specimen, a process called drawing. This process can be observed without the need for a testing machine by stretching a polyethylene six-pack holder. Not all polymers are able to sustain this drawing process. It occurs when the necking process produces a strengthened microstructure whose breaking load is greater than that needed to induce necking in the untransformed material just outside the neck. During yield and the plastic flow regime following yield, the material flows with negligible change in volume. Increases in length are offset by decreases in cross-sectional area. Strain energy. The area under the stress-strain curve up to a given value of strain is the total mechanical energy per unit volume consumed by the material in straining it to that value. In the absence of molecular slip and other mechanisms for energy dissipation, this mechanical energy is stored reversibly within the material as strain energy. When the stresses are low enough that the material remains in the elastic range, the strain energy is just the triangular area under stress-strain curve. Strain energy increases quadratically with the stress or strain, i.e., that as the strain increases, the energy stored by a given increment of additional strain grows as the square of the strain. This has important consequences, one example being that an archery bow cannot be simply a curved piece of wood to work well. A real bow is initially straight, then bent when it is strung. This stores substantial strain energy in it. When it is bent further on drawing the arrow back, the energy available to throw the arrow is very much greater than if the bow were simply carved in a curved shape without actually bending it. The area up to the yield point is termed the modulus of resilience, and the total area up to fracture is termed the modulus of toughness. The term modulus is used because the units of strain energy per unit volume are Newton per meter square, which are the same as stress or modulus of elasticity. The term resilience alludes to the concept that up to the point of yielding, the material is unaffected by the applied stress, and upon unloading will return to its original shape. But when the strain exceeds the yield point, the material is deformed irreversibly, so that some residual strain will persist even after unloading. The modulus of resilience is then the quantity of energy the material can absorb without suffering damage. Similarly, the modulus of toughness is the energy needed to completely fracture the material. Materials showing good impact resistance are generally those with high moduli of toughness. During loading, the area under the stress-strain curve is the strain energy per unit volume absorbed by the material. Conversely, the area under the unloading curve is the energy released by the material. In the elastic range, these areas are equal and no net energy is absorbed, but if the material is loaded into the plastic range, the energy absorbed exceeds the energy released, and the difference is dissipated as heat. In conclusion, TE stress-strain curve is crucial because it visually maps a material's mechanical behavior, revealing key properties like stiffness, Young's modulus, strength, yield, and ultimate tensile strength, and ductility, elongation, essential for selecting materials, designing safe structures, optimizing manufacturing, and analyzing failures, ensuring components perform reliably under load.